This will be the last lecture in the confidence intervals unit. In the previous two lectures, we talked about confidence intervals for distributions where we were finding the mean, okay? So for this one, we're looking for confidence intervals for proportions, not for means. And specifically, we're going to be working with binomial distributions, okay? So let's remind ourselves a little bit as to what binomial distributions are. So it's a binomial experiment. Remember, a binomial experiment only has two possibilities. It might be positive or negative, yes or no, you have it or you don't have it. Success or failure is what we typically refer to them as. So those would be our two outcomes, and we're going to continue to refer to them as success or failure. And how we define success and how we define failure is going to be based upon the experiment and what the different outcomes are. Okay, so two outcomes. And the other thing about a binomial experiment is, if you remember, P is referred to as the probability of a success. And Q is 1 minus P, and that's the probability of a failure. So when we talk about the probability of a success, this is also called the population proportion. Okay, so P, I'm going to put this in a different color because it's going to become really important for this particular lecture. Okay, think of it as the proportion of successes in a population. So you'll see this a lot in the examples that we're going to do, but it might be if you're testing 1,000 products, how many of them work? So it might be that 900 out of 1,000 products are working products, and that would be your population proportion. So it's the proportion of successes in the whole population, exactly what it says, population proportion. So we're going to create confidence levels for this population proportion. Okay, and in order to do that, we need exactly the same thing. We need a point estimate. Okay, so for the mean, when we were doing confidence intervals for the mean proportion for the mean of the population, the point estimate was the mean of the sample. So here it's the same thing. If we're creating a confidence interval for the population proportion, the point estimate is the sample's proportion. So it requires a point estimate for P. So what is this? Again, this will be the proportion of successes in a sample. Okay, we refer to this as p hat. Okay, that's how we read it. So it's p with a little hat on it. Okay, so what does this mean? Okay, so I want you to go back to that coronavirus study. Sorry, I don't know where this line came from. Like I said, that sometimes happens. I want you to go back to that coronavirus study that I was talking about in some of the previous lectures. I think I talked about it in the first lecture in this unit. So New York State conducted a coronavirus study when I'm doing this lecture. It was last week. And what they did is they randomly tested 3,000 people to see if they had antibodies for the coronavirus. So this is a binomial experiment. Either they do have the antibodies or they don't, okay? And from it, what we're doing is we're estimating the proportion of successes in the population. So what do we mean by that? We're saying, okay, well, based on the percentage of successes meaning positive antibody tests, based on the number of positive antibody tests in the sample, how many positive antibody tests do we think would be in the population? Okay, and they found that the number of positive antibody tests in the sample was 13.9%. And they said, okay, well, that means that it's 13.9% in the population. But remember what we said about these point estimates. They are almost never the same as the actual number for the population. So the point estimate for the means is almost never the actual mean for the population. And the same thing holds true here. The point estimate for the proportion of successes in the sample, right? Let me rephrase. The proportion of successes in the sample, which is our point estimate, is almost never the same as the proportion of successes in the population. So we need to create this sort of confidence interval. Okay, so let's talk about how we would do that. And we're going to create a confidence interval based on this real data that they found. Okay. Sorry, I'm just checking that we... Okay, so before we do that, let's take another example, okay? So the first thing that we need here is a binomial experiment, okay? Because we need yeses or nos. We need success versus failure, because otherwise how do we calculate the population proportion is based on percentage of successes. So either it's a success or it's failure, okay? So let's do some calculations here. So p hat is equal to x over n. So what does this mean? X is the number of successes in the sample. And n is the sample size. So this is the exact same thing that we had when we were doing the binomial distributions, right? In the binomial distributions, X represented the number of successes, N represented the sample size. And Q hat, which is the percentage of failures, okay, the proportion of failures in the population, not surprisingly, is 1 minus P hat. It's only a percentage if we multiply by 100. Otherwise, it's just a proportion. Okay. And the other thing that we need to do is we need to figure out what the margin of error is, right? When we create a confidence interval, we're taking the point estimate and we're either adding the margin of error and subtracting the margin of error, and that will give us the confidence interval. So the margin of error for a population proportion is a little bit different than the margin of error for the mean. So it's Z sub C. So again, our binomial distribution is approximating it's approximating a normal distribution. That's the assumption that we're working on here. And it's P hat, Q hat, over N. And you take the square root of that. Okay, and that is what the population, the margin of error for the population proportion is. Okay. Okay, so let's just do an example, just figuring out sample proportions, and then we'll go in and we'll actually create some confidence intervals, okay? So we're just starting with sample proportions, just so that you get accustomed to that part, and then we'll add in, okay? So in a survey, of 1,550 US adults, 1,054 said they use Facebook. Let's find the point estimate for the population proportion. Okay, remember what this is. This is just the sample proportion. So P hat is equal to X over N. Well, we need to figure out what X is. So X is the number of successes. There are 1,054 successes, 1,054 people who said, yes, we use Facebook. And then N is the sample size. N is the number of people who are asked, which is 1,550. So the sample proportion is 1,054 over 1,550, which is 0.68, or 68%. So P hat is 0.68, but we're saying that 68% of US adults, based on this, our point estimate is 68% of US adults will use Facebook, okay? So we're making a generalization about the population. But again, this generalization is not really true because the population proportion is almost never the same as the sample proportion. So that's the whole point of developing these confidence intervals, okay? Let's take another example. Let's say that we conduct a poll of 823 people. And we ask them if they'll buy shoes online. And we find that of the 823 people, 516 say yes. So once again, we want to find the point estimate for the population proportion. So notice we're not finding any confidence intervals yet. Well, here, once again, we need to figure out how many successes there are. So the number of successes is 516 because that's the number of people who said yes. But then we also need our sample size. And we asked a total of 823 people. So we say P hat, okay? And the P hat is what tells us that it's a sample proportion and not a population proportion, okay? It's our way of distinguishing between the data so that if you see a P hat, you know it's just a sample proportion. And if you see just a P, then you know that it's a population proportion, okay? So P hat is the number of successes over the sample size, which is 516 over 823. And if we plug this into a calculator, we get 0.63 or 63% of people. That's a 63. These are threes, not eights. So let me rewrite that. Okay, hopefully that's clear. 63% of people say that they buy their shoes, that they would buy their shoes online. Okay. But again, this is not accurate because this is based on the sample. And it's very unlikely that if we asked every single person in the population, that exactly 63% would say that they would be willing to buy shoes online. So we have to create this confidence interval, okay? So let's do this, okay? So there's some things that we have to assume. We have to assume that the estimation process is repeated a very large number of times, okay? The bigger the sample size, the more accurate our calculations. So let's just put some of these things in, some of these requirements, okay? And when we do this, you also have to check for some things like we did with the mean, with the confidence intervals for the mean, okay? So the first thing is we want to repeat the process a large number of times. Because the bigger the sample size, and this is always true, that when we have a larger sample size, our calculation is more accurate. If instead of asking 823 people, we only asked 5 people, then it might look like it's only 20% or 40% instead of 60%, okay? So the more accurate the calculation. The other thing is, and you could see this from what we said about the margin of error, a binomial distribution can approximate a normal distribution. So it needs to be able to approximate this normal distribution, or we can't use this idea of a z-score, right? This idea of area under a curve. And remember, the area under a curve is a proportion. It's the proportion of the area that we're using versus the whole area that's under the curve. So in order to move ahead, we always have to make sure that we actually are approximating a normal distribution. So a binomial distribution can approximate a normal distribution. And this is what we'll have to check for. I'm going to rewrite this underneath. Ran out of room. One, and I'm going to put this in a different color because it's so important. When NP is greater than or equal to 5 and NQ is greater than or equal to 5. So in the other cases, we were saying, okay, well, either the population approximates a normal distribution, the data from the population, okay, or N had to be greater than or equal to 30. That's what we were checking for. Here, we're checking to see that NP is greater than or equal to 5 and that NQ is greater than or equal to 5, because that's when it approximates a normal distribution. Okay, here's the other thing that we can say. When NP hat is greater than or equal to 5 and NQ hat is greater than or equal to 5, Okay, so when both of those things are true, the sampling distribution of p hat, and we'll explain this in a second, is approximately normal with a mean of the population proportions or sample proportions that is equal to the population proportion. Okay, let's clarify what this means because that just seems complicated. Okay, if we take 20 samples, all of size 3,000, and for each one we take a sample proportion, and then we take the mean of those proportions, we're going to get the population proportion. Okay, so if we take the mean of all of the sample proportions, we're going to get the population proportion. Okay, so let's write that down so that when you look at these notes later, you will understand what we're talking about. So if we take 20 samples of 3,000 people, and for each one we find the sample proportion. Okay, so the number of successes over the sample size, which would be 3,000 in each of these cases. That's going to give us 20 numbers. Okay, the mean of all the different p hats would be the population proportion. Okay, in other words, the mean of p hat is equal to p. Okay, now we also have something called a standard error, which is the standard deviation of all of those. So the standard deviation, also called the standard error, is the square root of p times q over n. So we have a mean and a standard deviation here. Okay, so what does this mean? This means that we could find a z-score. Okay, so we could find a z-score. We have a sample proportion and we have a sample size. So that means that we can construct the confidence interval. So it's exactly like what we've done in the past. It's just that we're using different numbers. Okay, so what we're going to do is we're going to create a 95% confidence interval for the information about US adults and their use of Facebook. Okay, so let's go back. I'm going to put this information in again because this way you have it in front of you again. So the information about Facebook was there were 1,550 adults were asked if they used Facebook. We said that 1,054 said yes. What we want to do is we want to create a 95% confidence interval. For the population proportion. Okay, so what do? Exactly the same thing that we did with population means. Okay, first thing that we do is we find the point estimate. So we already did this, right? P hat is 1,054 over 1,550, which we found to be 0.68. Once we have P hat, we have to check to see if this approximates a normal distribution. Because remember, z-scores are based on a normal distribution. You cannot use z-scores without that. So this is really important. And here it's not going to tell you. Okay, you're not going to see it in the data, in the question where it says this is a normal distribution, because it's not, it's binomial. So what are you checking for? You're checking to see that NP hat is greater than or equal to 5, and you're checking to see that NQ hat is greater than or equal to 5. So we would want to find Q hat. So remember that Q hat is 1 minus P hat, or 1 minus 0.68, which is 0.32. So we need to find Q hat. We're going to be using it in our formulas. We need it in order to see if it approximates a normal distribution. Okay, so our N is 1,550. So we're going to do 1,550 times 0.68. Okay, this is equal to 1,054. And yes, this is greater than or equal to 5. So we're okay there. Now we're going to do 1,550 times 0.32, and we get 496. 496 is also greater than or equal to 5. So we're okay there. Okay. Now we need to find the z-score. Okay, so how do we do this? It's a 95% confidence interval, okay? Our C is 0.95, right? So if our C is 0.95, we need 1 minus C, which is 0.05. And that 0.05, if you remember, is the percent that's outside the interval. Okay, we're going to take that 1 minus C and we're going to divide by 2. And I'll show you on the diagram again what we're looking at. This is 0.025. So if you remember from our normal distribution, what we're saying is, here's our interval. Inside here is 95%. Now our z-score, it gives the area to the left, right? So in order to find our z, what we're going to do is we're going to figure out what the area to the left of here is. So if 95% is in the interval, the remaining 5% is to the left and to the right. We only want what's to the left, and this is symmetrical. So we only want this piece here, and this is 2.5%, okay, or 0.025. So now we go to the z-score chart. Remember, this is also referred to as the standard normal table. So remember, here you're looking for the z-score. You're given the area and you're looking for the z-score. So when you're given the area, you're looking at the inside of the chart. Now we've done this before with a 95% confidence interval, but let's go to the z-score anyway. We're at 0.025, so we're going to be in the negative. We'll always be in the negative, but remember when we look at the z-score, we're going to take the absolute value. So at 0.025, if we look for that number, we're right here. I'm going to try this. 0.025 is right here. Okay, that's where 0.025 is. So 0.025, I covered it up, but if we look for it, okay, here's our 0.025. That gives us negative 1.96. And remember, we just want the z, so we take the positive. So our z is equal to 1.96. Okay, so we ignore the negative. We only take the positive value. Okay, z is equal to 1.96. Okay, so what do we do with this? We find the margin of error. So from before, E is equal to the z-score times the square root of p hat q hat over n. So this is 1.96 times the square root. P hat, we already said, is 0.68. Q hat is 0.32. And our sample size is 1,550. So we get 0.023 is our answer. That's our margin of error. And the last step is construct the interval. So remember, we take the point estimate, which is p hat, and we add the margin of error. So in this case, p hat was 0.68, and we add 0.023, which is 0.703. And then we take p hat, and we subtract. I have to move this because you can't see it. We take p hat, and we subtract 0.023, or we subtract the margin of error. Which is 0.68 minus 0.023, which is 0.657. So that means that's somewhere between 65.7% and 70.3% use Facebook, okay, with 95% confidence. So it's not exactly 68%. It's somewhere between 65.7 and 70.3. So let's go back and just review what we've done so far, okay? So the first thing is that we're creating a confidence interval for a population proportion, which means what is the percentage of success in the population. So we created a point estimate. Point estimate is whatever proportion we find from a sample. Then what we're looking for is to see if the sample is an approximate of the normal distribution. And it is. How do we check for that? We check and make sure that the sample size times the sample proportion is greater than or equal to 5, and that the sample size times the proportion of failures is greater than or equal to 5. And if it is, then it approximates a normal distribution, so we can go ahead and find z-scores, okay? Now, in order to find the z-score, we have to know what the confidence interval is. So here we were told that the confidence interval, the level of confidence, is 0.95. So 0.95 is within the interval. We found the area outside of the interval because in order to find the z-score, we're only looking at areas to the left, okay? So the area outside the interval is 0.05. We want only half of that. We only want the area on the left, so we divide it by 2. Then we went to our z-score chart. We found the corresponding z-score for an area of 0.025, and we got 1.96. Remember, you just take the positive value. Then we found the margin of error, because the margin of error is what's going to give us the actual interval. So we took the z-score and we multiplied by the square root of p hat q hat over n. Very similar to what we did in order to find the margin of error when we were looking at confidence intervals for means. This told us the margin of error was 0.023. So we took our point estimate and we added the margin of error, and we took our point estimate and we subtracted the margin of error. What this tells us is it's very unlikely that the population proportion is 68%. There's a 95% chance that it's going to fall between 65.7 and 70.3%. Okay? So that's what we did. We're creating an estimate, and then we're saying it's going to fall within this interval. Okay? So let's go and let's do another one. Okay? Let's go back because I said that we were going to do this. Let's take the experiment with coronavirus testing, okay? And they said that the sample size was 3,000 people. So in New York State, 3,000 people were tested for antibodies for the coronavirus. And what we want to do is the same thing that we did before. Okay, we're going to construct a 95% confidence interval. So the sample proportion was given to us, okay? They said 13.9% tested positive. So the sample proportion, p hat, was equal to 0.139. That's what 13.9% is as a decimal. So we want to construct a 95% confidence interval. For the population proportion. And it is really important to understand that when you get a number like this, you can't just assume, oh, well, that means that 13.9% of the population tested positive for would test positive for antibodies. That's actually really unlikely, but we could create a pretty good interval, okay? And all of this assumes that it's a random sample. Okay, and they said it was a random sample here. Some people might argue, well, it wasn't really random. The way that they did it is they collected samples from people who were in grocery stores or box stores, some of the big box stores like Target. So one might argue, well, is that really random? It was as random as they could do it based on what they were doing. Okay, so we were already given the point estimate, so we don't have to do that again. Okay, point estimate. So p hat is equal to 0.139. So the first thing that we have to do is see if it approximates a normal distribution. You always have to remember to do this. When you find the z-score, that should remind you. So this is where we find our NP hat and our NQ hat. So this is 3,000 times 1.39, sorry, 0.139. And this gives us 416, and 416 is greater than or equal to 5, so we're okay there. I'll put Q hat up here. Q hat, we just subtract P hat from 1. It's the opposite, right? Proportion of failures is the opposite of the proportion of successes. So 1 minus 0.139 is 0.861. So we're going to do N times Q hat. So 3,000 times 0.861. And you can see that if 3,000 times 0.139 is 416, then this is 0.869 is going to give us a higher number. So this is going to be greater than or equal to 5, and it is. If you put it into your calculator, it's 2,583. Okay. So now we're going to find our z-score. So we know that z sub c is equal to 1.96. So we know this from the previous problem. So we don't have to calculate it again every time. Now, if you're on a test, you can always say that you know it from previous problems. But for the very first problem that you see, you should calculate it. Okay, you should go through what we did before, where we said that c is equal to 0.95. So 1 minus c is 0.05. You divide that by 2. You're looking up 0.025 in your z-score table in order to find that z-score. Okay. Then we do the margin of error. So our margin of error is z sub c times the square root of p hat q hat over n. So it's 1.96 times the square root of 0.139 times 0.861 over 3,000. And if we plug this into our calculator, we get 0.012. So now we find our interval. So we're going to do p hat plus our margin of error. And p hat was 0.139. So if we add 0.012, this gives us 0.151. And if we subtract our margin of error, so minus 0.012, then we get 0.127. So our interval says 0.127 is less than p, because we're talking about the population proportion, which is less than 0.151. So here's what this tells you. There is a 95% chance that somewhere between 12.7%, so we're turning it into decimals, and 15.1% of the actual population of New York State I should say will test, because we didn't actually test them, will test positive for coronavirus antibodies, okay, which is very different, okay? And we might say, oh, well, what's the big deal? 13.9% versus 15.1%, but it is a big deal because when you're talking about 19.1 million people, that's a very large difference in the numbers, okay? So it's important that we remember that it's not exact. Okay, and in fact, what we'll do is we'll figure out what a 99% confidence level would be. Okay, so let's do the same thing, but this time we're going to construct a 99% confidence level. And what that means is we don't have to do all of this again. All we have to do is from here down. We have to find the z-score and then the margin of error based on that z-score. So we're going to construct a 99% confidence level now. Okay, so again, this means that p hat is equal to 0.139. Q hat is equal to 0.861. I'm going to write it here that we already checked. That n p hat was greater than or equal to 5, and that n q hat was greater than or equal to 5. Okay. So C this time is equal to 0.99. So we need to figure out what the z-score is based on the level of confidence. So once again, we have to figure out what part of the area is outside the interval. So 1 minus 0.99 is 0.01. And then we're going to take 0.01 and we're dividing by 2 because we only want the area on the left. Okay, so this gives us 0.005. So this is the area to the left of the interval. This is the number that we look for in the chart. Okay, so let's do that. Let's go to the z-score chart and find 0.005. So we know that we're going to be in the negative numbers, but, okay, we're going to take the positive value at the end. So 0.005, here's 0.0012. 0.005 is exactly in between negative 2.57 and negative 2.58. And again, we drop the negative sign. Now, since it's exactly between, usually we take which one it's closer to, right? But since it's exactly between, we have to actually calculate what would be exactly between. So some of you will be able to see this right away, that it's 2.575. But if you can't, just divide by 2. Add and divide by 2. You're taking the average. Okay. So what's the margin of error? It's z sub c times the square root of p hat q hat over n. So we have 2.575 times the square root of 0.139 times 0.861 over 3,000. So let's go and calculate that. I didn't do this ahead of time, so I will do it here with you. Okay, so we're doing 0.139 times 0.861. Okay, we're dividing that by 3,000. That's the n hat p hat over 3,000. Now we have to take the square root of that. So we have second, and then we have square root. Okay. And now we multiply by the 2.575, by the z-score. And we get 0.04187. So we can round to 0.04. Okay. You can even go as far as 0.042. But since I would do 0.042, the only reason why I would do 0.042 instead of just 0.04 is because this goes to the third decimal place. So this should go to the third decimal place as well. Okay. So we can construct our interval. P hat plus the margin of error. I'll label these also. This is step 1. This is step 2. We said we find the z-score is step 3. Margin of error is step 4. And then finding the interval is step 5. So we have 0.139 plus 0.042. And we get 0.181. And then we do 0.139 minus 0.042. That's the lower end of our interval. And we get 0.097. Okay, and look at the huge difference in interval here. This is saying 0.097 is less than P, which is less than 0.181. Okay, in other words, there is a 99% chance that between 9.7% and 18.1% of the population test positive for antibodies. So now the question is, okay, well then how accurate is this? This is a huge range, 9.7% versus 18.1%. Okay, so to be 99% sure, it's going to give us a much bigger range. Now, typically, I've said this before, we look at 95% confidence intervals. Okay, now here's the thing though. Part of this has to do with the sample size. Okay, so if we want a certain confidence level and a certain margin of error, we might want to know what our sample size should be. So let's go through that. We've done this before, actually. We did it in the first lecture on confidence intervals when we were looking at intervals for means. Okay, so let's figure out a good sample size. Okay, now in order to do this, we're going to do exactly what we did before. We're going to use the formula for margin of error. So in this case, you're being given a margin of error and a level of confidence. So let's figure out a good sample size given a margin of error and a level of confidence. Okay, and this can be done based on that formula. So that formula is essentially what we're doing is we're solving the formula for margin of error for n. We're going backwards. So let's do that. Let's go through the algebra so that you see where it's coming from. Sorry. Okay. So how do we do this? I'm going to go through the algebra with you. If you get a little lost, that's okay. I'll try and be very clear about it. It's okay if you get a little bit lost. The point here is just to tell you where the formula comes from so that you kind of see what's going on. So just try and follow along as to what I'm doing here, but don't feel like you have to reproduce it necessarily. Okay, so the first thing that we want to do is we want to get rid of that square root because that part is going to cause us a problem. So we have lots of different ways that we could do this. I'm going to recommend that we get rid of the square root first, just because, no, I'll do it differently. Let's get rid of the z sub c first, okay? So we're going to divide both sides by z sub c. Okay, the reason for doing that is that then we isolate the square root. Okay, so now what we have is e over our z-score is equal to the square root of p hat. The hat goes on top of the p, which is why it's called p hat. P hat, q hat over n. Okay, now we can score both sides. Okay, that's going to get rid of the square root. And I'm going to rewrite it like this, where you distribute the square. You're allowed to do that. Okay, what that does for us is it keeps the e and the z-score separate so that we don't have to worry about it always being linked together. So this is p hat q hat over n. And now what we could do is we can multiply both sides by n, and that'll get rid of the n in the denominator. So we've done this before. We did it the last time that we tried to solve for n. We multiply both sides by n to get it out of the denominator. So it cancels here. Now we're left with n e squared over z squared, which is equal to p hat q hat. And then what we could do is we can multiply both sides by the reciprocal of this, because then the z will cancel, the e will cancel on this side. So we're going to multiply both sides by e squared over z sub c squared. Sorry, the reciprocal. Z sub c squared over e squared. Because then the e squared will cancel and the z sub c squared will cancel here. Okay, and what that means is that that gives us our final formula. So n is equal to p hat times q hat over, and now we could just put this all together in one set of parentheses, z sub c over e squared. Okay, so the other thing here, and we said this before when we talked about sample size, if n is not a whole number, which it rarely is, then you want to round up. So just include the full person, essentially. Okay, so let's take the coronavirus again. Okay, we're going to do two different examples. Let's do the first one. Let's, again, with coronavirus. Okay, this is the reason why I'm doing that is because it's such an apropos example in this case that it kind of seems silly to leave it out. Okay, so what would be a sample size that would make us 95% confidence that the margin of error is within 0.001, okay? Given, again, the same data, p hat is equal to 0.139. So the point estimate is the same, okay? So here, we have to go through that same exact process, okay? So p hat, this is like our 1, p hat is equal to 0.139, q hat is equal to 0.861, n times p hat, well, n we don't know, so we're assuming that it follows, we're assuming that it's a normal distribution, that it's going to follow a normal distribution, because we're using, the reason why we're saying that is because we're using the z-score, okay? We don't know what n is, we're looking for it. Okay, so what we're going to do next is we're going to find the z-score. So I'll put this in here. C is equal to 0.95. 1 minus C is equal to 0.05. And 0.05 over 2 is 0.025. So our z-score coming from the table is 1.96. So we did this already. Okay. Now we know that our margin of error is 0.001. So now we find the sample size. So it's less work here, okay? So E is 0.001. So using the formula that we just came up with, N equals P hat Q hat times Z sub C over E squared, we're going to say N is equal to 0.139 times 0.861 and then 1.96 over 0.001 squared. So in order to have a 99% confidence interval that it falls between 0.138 and 0.140, we need 459,000 people, 459,759 people to be 99% sure that the percent of the population that tests positive is between 13.8% and 14%. So notice 3,000 is nowhere near that, okay? So, and this is just to be 99% sure that it's between 13.8 and 14. It's not even that it's exactly 13.9. So you can see that 3,000 people is actually not that many people, okay? Okay, let's take one last example. And again, this will just to be for sample size. So in this one, you're running a campaign and you want to know what percent of voters will vote for your candidate. And they do this all the time, right? When they report on polls, that's what this is. It's a population proportion estimate, and they don't give you confidence intervals, right? Sometimes they will, but most of the time they won't. So, but the confidence intervals are important, okay? So your estimation is for the sample sample proportion is 0.41. Okay, just so that you know, and I'm going to put it back on the other page. If you don't have a p-hat, so maybe you didn't start out with an estimation, you don't have it, then use p-hat is equal to 0.5. Okay. it's going to give you a much larger sample. You're going to have to use a much larger sample, but you can use p hat equal to 0.5. Okay. Find the necessary sample size if you want to be within 3% of the population proportion with a 95% confidence level. Okay, so what does this mean? Our p hat is 0.41, which means our q hat is 1 minus 0.41, or 0.59. Okay, our c is equal to 0.95, and we already know from our previous problem that z sub c is then 1.96. And our e is equal to 3%. 3% is 0.03. So this was 3 divided by 100. You need it as a sorry, I lost my train of thought. You need it as a decimal. Okay, so what's our sample size? N is going to equal p hat, which is 0.41, times q hat, which is 0.59, and then times 1.96 over 0.03 squared. And what this tells you is that you need to ask 1,033 people. Okay. Now, if we started off with p hat equal to 0.5, it's not going to be all that different because 0.41 is very close to 5. But here, if we didn't have a p hat, okay, this would have been a very different number. We would have had a larger number in order to be within 99% sure. Okay, so this should be a q hat up here. But what this does is it gives you some idea as to how many people you need to ask. In the case of this sample size of this case, okay, where they're talking about coronavirus data, 459,759 people may not have been realistic. So they might have said, okay, well, we don't care about a confidence interval where the margin of error is 0.001. It's okay if the margin of error is 2.3%. So they figured out that to have a 2.3% margin of error, as opposed to this is a 0.1% margin of error, to have a 2.3% margin of error, they only need 3,000 people, and that's a lot more realistic for the number of antibody tests that they have. Okay, they don't have close to 500,000 antibody tests. So that's why they do this, and how they decide on the sample size is they say what's an acceptable margin of error. And for this particular case with the coronavirus, it might have been that an acceptable margin of error was maybe 2.3% or 2.5%, whereas, and that has to do with the limitation of what they have available. If they don't have 500,000 tests available, they can't have a margin of error that is that small. So they're going to do a bigger margin of error, and so they only have to do 3,000 tests. It's a much bigger difference. Okay, so that's a confidence interval for population proportions. So remember, it's a binomial experiment, so it's either a yes or a no, a success or a failure. Okay, positive or negative. You need to double check that it will approximate a normal distribution by doing NP hat and NQ hat both greater than or equal to 5. We didn't have to do that here because there is no N. That's what we're looking for. Okay. You're finding the z-score using the confidence level, and then you're finding the margin of error based on that z-score. You're adding it, you're subtracting it. That's what gives you the confidence interval. Okay. And that's it for confidence intervals. So this is the last lecture in the unit. It's only 3 lectures.